This is a walkthrough of Problem 1 on Exam 1 of Module 5 in the book Problem Solving Guide for Mechanics and Thermodynamics. 1 kilogram mass is attached to a light elastic cord with a length of 80 centimeters. That's the relaxed length. The cord has a stiffness of 20 newtons every meter. It is attached to the ceiling of a physics lab. The mass is released from rest at the ceiling. How fast is it moving after it falls? 80 centimeters. How fast is it moving after it has fallen 120 centimeters? So let's start with a good diagram. The mass is released from rest here. It falls 80 centimeters. Then the string gets taut and the string stretches and it keeps going down to 120 centimeters. We need the speed here at 80 centimeters, the speed here at 120 centimeters, knowing it was released from rest. And the cord has a relaxed length of 80 centimeters. So let's calculate the work done by the gravitational force on the mass after it falls 80 centimeters. The work done by gravity is the force of gravity times the distance moved in the direction of the gravitational force, which is downwards. Substituting in the numbers, the weight of the mass is 10 newtons. 0.8 meters is the distance in meters. We get 8 joules for the work. That's the only force that does work on it. The cord is not stretched, and we're ignoring air drag. The total work done is 8 joules. The total work done is the change in kinetic energy, and that's 8 joules because it started at rest. The work is delta KE, KE final minus KE initial, and KE initial is 0. It was released from rest. So all we have is 8 joules is the final kinetic energy, and we can solve for the final speed. It's 4 meters per second. So it's going 4 meters per second right here. That's the answer to part A. Because the acceleration is constant, we can use a kinematic equation. V final squared equals V initial squared plus 2AY. Y is 80 centimeters, A is 10 meters per second squared, V initial is 0. We can solve for V final, and it's, of course, 4 meters per second. On to part B. Here the mass has fallen 120 centimeters, the work done by gravity, the same expression, mg delta y. Here, delta y is 120 centimeters in the direction of the force. Gravity made a deposit of 12 joules into the kinetic energy of that mass. The cord is exerting an upward force, and this force is increasing as the cord stretches. The gravitational force is always 10 newtons during the fall. The cord is stretching, the force gets bigger. The work done on the mass by the cord is 1/2 kx squared. There's a negative sign there to remind us that it's slowing the mass down. The stretch is 0.4. X in this equation is the distance the cord is stretched. So we get minus 1.6 joules. The total work done by all the forces on the cord during the 120 centimeter fall is plus 10.4 joules, plus 12 for gravity, minus 1.6 joules for the cord. The change in kinetic energy is the total work done, which is plus 10.4 joules. The drop from rest, we can solve for the final speed. And we get 4.56 meters per second. So it's going 4 meters at 4 meters per second after it fell 80 centimeters, 4.56 after it fell 120 centimeters. Initially, it might be surprising that it's going faster. The cord's slowing it down, right? Well, actually, it's pulling up on it, but it's not yet slowing it down. To see what's going on, let's calculate the net force on the 1 kilogram mass when the cord is stretched 40 centimeters. The force is Kx. K is 20 newtons every meter. It's stretched 40 centimeters, 0.4 meters, and we get 8 newtons. Let's put that on the force diagram. The tension in the cord is 8 newtons at this point, and it's getting bigger because the cord is stretching. What's the force of gravity on the mass? Well, it's always 10 newtons, so let's put that on the force diagram. It looks like the net force is 2 newtons downward, which means it's accelerating downward. It's still speeding up. So don't be tempted to use an equation like this at this point, 1/2 at squared. This equation was derived assuming the acceleration is constant. The acceleration is not constant because the force isn't constant, because the force depends on how much the string is stretched. So if you look at this, 20 newtons every meter, in order for the force to be 10 newtons, it has to stretch 1/2 meter. So as soon as it falls 50 centimeters, then it starts to slow down thereafter because the tension in the cord will be bigger than the gravitational force. That's problem 1.